Okay, well, welcome everybody. This is our second session of the AI Winter Workshop hosted by Brown Center for the Fundamental Physics of the Universe. I'm Jonathan Pober, and together with Dr. Madhurima Chowdhury, we're going to tell you about training simulations to predict the first stars and their effect. So the next 45 minutes or so, I'll give you an overview of this field. And for those who are new to cosmology or radio astronomy, kind of give you a sense of the problem at hand and some of the applications of machine learning that researchers are exploring to this field. And then we'll spend an hour and a half. Well, I should say, following that, I'll take questions. So as you're listening along, post questions in the Q&A. And I'll spend a few minutes going over questions before we segue into more of the workshop portion of the session. And Dr. Chowdhury will walk through an example of some of the machine learning techniques at use in this field of 21 centimeter cosmology. And I'll explain that name, 21 centimeter cosmology, in just a moment. But so again, please, if you've got questions as we go along, post them in the Q&A, and we'll have a little bit of time to go over those when I wrap up. So, as I said, the outline of this first presentation part is to explain what this field of 21 centimeter cosmology is. What are we trying to do? What is it that we're trying to measure? What physics are we researching? And then to go over the measurements that these experiments actually make so we can understand the data that we're looking to apply AI and ML techniques to. And then I'm going to focus on two very actively researched applications of ML AI techniques to this field. One is the identification of contaminated data. So we have a large issue with data contamination, and we need to exclude it from our analysis. And then at the other end of kind of the pipeline, interpretation of the measurements. If we actually succeed in one of these experiments, how will we get physics back? So to start off with, what is 21 centimeter cosmology, and what does it have to do with the first stars? Well, for those of you who are here in this morning's session or just generally familiar with particle physics, you may have heard of the standard model of particle physics, which is this beautifully explanatory model describing the fundamental constituents of nature, bosons and leptons and quarks. There's a very, very nice symmetry between these particles. They describe basically everything that we see coming out of particle colliders like the LHC. It's an incredibly powerful, incredibly accurate theory describing the fundamental nature of our universe. In cosmology, we use the term standard model to mean something a little bit different. So when you ask a cosmologist, what is the universe made of? Well, we say we kind of have a basic picture, a standard model, where most of the universe is made up of something called dark energy. Most of the remaining universe is made up of something called dark matter. And then only a very small portion of the universe is made up of the ordinary matter. And so this yellow piece of the pie is what is described by the standard model of particle physics. The other 95% of the energy density of our universe is more or less a mystery to us. And that's what cosmologists really want to understand. We see evidence in the structure and the evolution of our universe for this 95% dark matter and dark energy, but we don't know what they are. And understanding what most of our universe is made of is a grand challenge in cosmology. One particular era of interest is what's called the epoch of reionization. So I'm going to play a movie here. It's a simulation of cosmic histories. And so as time goes on, we're progressing this simulated volume of the universe forward. And what's happening, you see this black box with these slowly growing blue regions, expanding and expanding. And so what this black box is the early universe. The black is neutral hydrogen gas, the most abundant element in the universe. And what you see is it's being eaten away, it's being destroyed as these bubbles are growing and growing and growing. And those are bubbles of ionizing radiation produced by the first stars and galaxies in the universe. And this epoch of reionization is, in a sense, the moment in cosmic history when galaxies become important on a cosmic scale. So when stars actually feed back on the entire universe and turn all that neutral hydrogen gas into ionized hydrogen. And so studying the EOR is an opportunity to study not only the physics of galaxy formation and the physics of star formation, but how that dark matter and that dark energy setting up the structure in our universe led to this pattern of reionization from the first stars and the first galaxies that eventually formed. And so we want to understand this cornerstone of cosmic history, the moment when, again, this ordinary matter actually became important on a cosmic scale. The tool we're going to use to study that is hydrogen gas itself. So the 21 centimeter line is the spin flip transition or the hyperfine transition of neutral hydrogen. And so it's the very, very small energy difference between these two states of a hydrogen atom. So hydrogen atom is the simplest element you can have. It's a proton and an electron. As I said, it's the most abundant element in the universe. About 75% of that ordinary matter by mass is made up of hydrogen atoms. And there's this very small energy difference when the hydrogen atom transitions between these two states, where the spin, the quantum mechanical spin of the proton and the electron go from aligned to anti-aligned. And no matter what units you like to think of energy in terms of, electron volts, photon frequency, photon wavelength, their temperature, it's a very, very small energy. The wavelength of 21 centimeters is where the name of 21 centimeter cosmology comes from. And so what we're trying to do is study all the hydrogen in the universe. And since it's so representative of the ordinary matter in the universe, study the universe as a proxy, study it through this 21 centimeter line. And so this is what we would ultimately measure with this technique. This, again, is a simulation. It's not as beautiful a color scale as the previous simulation, but it's a very, very similar concept. A representative volume of the universe in 3 dimensions, and the signal we would expect to observe if we could see that 21 centimeter line from neutral hydrogen. And I'll explain a little bit more about what the patterns in here look like, but that's fundamentally what we want to measure. 21 centimeters is a radio wavelength photon. And so what we want to measure this with is a radio telescope. This is one antenna tile of the Murchison Wide Field Array, the MWA experiment in Western Australia. There's 16 antennas within one of these tiles, and then 256 of these tiles spread out across the Western Australian outback in the Murchison. And I'll explain why we're out in Western Australia in a little bit, but these are the tools we're using to make these measurements. And so when we say telescope, we're really thinking of arrays of antennas. And to map out this 21 centimeter signal, we get 2 directions on the sky. So X and Y in this image are, think of making a map of the sky. But what makes this such a powerful technique is that we get access to the 3rd dimension, the depth direction. And why that is, well, the universe is expanding. That's a fundamental tenet of modern cosmology. And so light emitted in the universe's past, as it travels through the expanding universe on the way to us, its wavelength stretches. And so, for example, if a hydrogen atom emits a 21 centimeter photon, when the universe was half its current size, by the time that photon reaches us, it won't have a wavelength of 21 centimeters. It'll have a wavelength of 42 centimeters. And so we can measure not just 21 centimeters, but all those wavelengths longer than 21 centimeters, we get the history of the universe along the depth direction. And that's why in this box, you see the signal changes over the z direction. The front of the box are photons that were emitted at a later time than the back of the box. The ones at the back of the box took longer to reach us, reach our radio telescope down in the corner there. And so we're seeing the universe earlier in its history when we look to longer wavelengths. And so this is the ultimate promise of this technique and why it's so exciting. 21 centimeter cosmology promises not just a map, but a three-dimensional tomographic image of all the hydrogen in the universe. And there's a tremendous potential to answer those fundamental physics questions about dark matter, dark energy, first stars, first galaxies, and more. It's a very exciting field for what it can ultimately deliver. It is also a very challenging field, and for the reason that we don't get to just see that box. And so I put here between us and the hydrogen signal we want to measure, a map of what the radio sky actually looks like. You go and image the sky, the entire sky in radio wavelengths, you see something like this map here. Most of what you see here is the Milky Way galaxy itself. This band running down the middle is the disk of the Milky Way, and we see these structures going off of it, but these are foreground emission. All sorts of other astrophysical radio emission that block our view of the hydrogen. And in a nutshell, that's why this is a challenging field, and that's why I'm talking about if we could measure a 21 centimeter signal, what this field could do for us, because separating the 21 centimeter signal from the foregrounds is so challenging. So a little bit more about the foregrounds. They're incredibly bright, like 4 to 5 orders of magnitude brighter than the 21 centimeter signal that we want to measure. The good news is that we understand the foreground emission. You can grab a textbook and see derivations of synchrotron emission and bremsstrahlung emission and the emission mechanisms that make these foreground radio signals. And as a function of frequency, so that's radio frequency or wavelength equivalently, the foregrounds don't change a lot. We often say they're smooth spectrum. They're not perfectly constant. They'll look a little bit different at 21 centimeters and 23 centimeters and 25 centimeters, but not a lot different. Whereas that 21 centimeter signal, the one from the hydrogen, as I said, as you look at longer and longer and longer wavelengths, we're looking at different parts of cosmic history. And so there's a lot of frequency structure or wavelength structure in that signal. And so it's that spectral behavior, the difference between these two signals as a function of frequency, that's going to let us distinguish them. And so, yes, pulling out a 1 part in 10 to the 5 little bit of frequency structure from a radio spectrum is challenging, but in and of itself, it's a manageable challenge for digital signal processing techniques. If we were given this data, radio signals where we said we've combined 21 centimeter signals and foregrounds, I could separate them and I could recover the 21 centimeter signal. There are other challenges, and that's what I'm going to talk about. Two, not the only two, but two of the challenges really facing this field and where machine learning and artificial intelligence techniques potentially have the most impact. The first one is that there's lots and lots of contaminated data. So what contaminates the data? Yes, there's the foregrounds. They're always there. You can think of them as contaminants, but that's not what we're talking about in this regime. What we're talking about here is what we call radio frequency interference. These are human-generated signals at radio frequencies. So if you convert 21 centimeters, and in particular, the epoch of reionization occurs when the universe is about 1/10 its current size. So we expect that 21 centimeter wavelength to be about 2 meters if we're trying to study the EOR. Convert that to frequency, and you'll find yourself in the FM radio band, 100 megahertz. At slightly higher frequencies, 160, 170 megahertz, there's digital television transmission. There's also satellite transmission, airplane communication, all sorts of human-generated radio signals. And those, I said the foregrounds are bright, 5 orders of magnitude brighter than the 21 centimeter signal. These RFI signals are even brighter than that. So we just have to remove them from our data. If there is a human-generated transmission in our data, set it aside, observe again, and get clean data. And we need a lot of data, but we just can't analyze data contaminated by RFI. And that is why the MWAs in Western Australia, another experiment in the field called HERAS in South Africa, very, very remote regions where human-generated transmissions are minimized by being far away from population centers. And so here's an example of some of our data. This is data from the MWA. What we see here in these plots, this is the signal versus time on the x-axis, and the signal versus frequency on the y-axis. And the color scale represents the strength of the signal. And what you see in this observation, it's not a particularly long observation, about 2 minutes of data. This black signal here at 146 megahertz and getting stronger and wider as the observation goes on, that's a human-generated transmission. You can ask an algorithm, go through all this data, right? This is only 2 minutes. It's pretty easy for you and I to see this signal, but when we get thousands of hours of data, each with thousands of plots like this every 2 minutes, identifying this by hand is hard. But algorithms have been written. This purple here is an example of contaminated data identified by this algorithm. All these other horizontal lines I should mention are contaminated. You can't see them here. That's a nice, unfortunate feature of the MWA system that we have to get rid of some of this data. But it's this blob here. The algorithm has found this signal and identified it as contaminated. We won't use that portion of our data. And so this was thought to be a solved problem. We thought algorithms like this worked, run it on all your data, and the radio frequency interference will go away. These algorithms were slow, and so machine learning was brought in as potentially a way to speed that up. And so this kind of identification of these RFI signals is a very good problem for machine learning. There's a couple interesting aspects of this. And so beyond a standard image-based analysis using a neural network, and we'll talk a little bit more about neural networks in a moment, but this architecture here, one of the issues, here's a plot of our data. There's that radio frequency interference signal. Standard, or the most basic machine learning image analyses are classification. This textbook example is always, is there a cat in the image? Yes or no? And so a convolutional neural network will reduce the dimensionality through convolutions of this input image, all the way down to a final yes or no answer. But with the radio frequency interference, we don't want a yes or no answer. We want a yes or no answer per pixel in the original image. It's not enough to say, yes, this image has radio frequency interference. We need to say, there's radio frequency interference here, and everywhere else is good. And so this architecture goes by the name of a U-net, where we go down one branch of the U, reducing the dimensionality to smaller and smaller, more abstract features, but then blow it back up to the full image. So we get a per pixel classification. Another fun bit is that radio telescope signals are complex numbers, and not just having an amplitude, but also a phase, or a real part and an imaginary part, but generally amplitude and phase is a more useful way to think of it. And so the architecture built in this paper is something of a double U-net, where the amplitude and the phase of the complex number go down separate paths before being blown back up to a single prediction. And so there were a lot of challenges in adapting kind of standard approaches for this, but it actually worked out quite nicely. The performance is pretty comparable to traditional methods, but ran about 20 times faster. And that was a big step forward. As our radio telescopes grow larger and larger and larger with more and more and more antennas, the radio frequency interference identification algorithms were actually becoming a major bottleneck of our analyses. And so speeding it up by a factor of 20 was in and of itself a big step forward. What kind of changed the game in RFI was the discovery of what we're now calling ultra-faint RFI. These are radio frequency signals, still human-generated signals, but not all that bright. In fact, fainter than the foregrounds. And so you can't really see them in extremely raw data right off the telescope because the foreground swamped them. But they're still much brighter than the 21 centimeter signal. And so what you're seeing here in this movie going by, this is an image of the sky, actually a very large area of the sky. We removed all the foregrounds, and what you see is this blob flying by on the left. Each one of these images, going by is a short amount of time, and what we've determined this to be is digital television reflecting off of an airplane flying over the MWA site. And so even though we're in Western Australia, far away from digital television stations, when an airplane is in view, television from below the horizon can come up, hit that airplane, and bounce down into our array. And so finding ways to identify signals like this, signals that humans and classical algorithms cannot see in the raw data, is a new challenge. We need a way to integrate the measurements, find these relatively faint signals, and remove them from our data because they're still so much brighter than the very, very faint 21 centimeter signal. And so that's an active area of investigation. The biggest challenge is that we have no ground truth when it comes to radio frequency interference. Meaning, if you give me some data and there's very faint radio frequency interference in it, I might not catch it. How can I possibly train a network to catch it if I can't label it correctly? And so what we see here are examples of real data where there's some bright radio frequency interference we can see standing out. And you can go and have an army of students and other people do their very best to hand label lots and lots of data for training a neural network. But you're probably going to miss something, especially that really faint stuff that we're now really worried about. Down here, we see simulated data where we've made mock data, put in mock interference, but these models are quite simplistic. We're not doing an electromagnetic simulation of digital television from below the horizon, coming up, hitting a conducting object like an airplane that's flying, bouncing back into our array. These are just very, very simple toy models. And if we want to train a network to find these ultra faint signals, those correlations in time, in position, in frequency that real signals will have are probably going to be very important. And so we're still working on this problem. How can we put everything we know about radio frequency interference into a single training set? I don't have an answer, but I would say that's probably the most active area of research where machine learning techniques are being applied to data from these radio telescopes. The second challenge I want to talk about, though, is kind of at the other end of our analysis. Let's assume, humor me, that these experiments worked perfectly. We got the foregrounds out of there. We removed all the radio frequency interference contaminated data. We got that beautiful map of the 21 centimeter signal. There it is again. What do I do with this? I explained that there's a tremendous amount of information in this map, or in this volume, this tomographic map. But if I want to know about dark matter or the first stars, how do I move from here to there? Well, machine learning is well suited to do a regression task here, where we're not asking to classify. We're not saying, is there 21 centimeter signal in this data, but rather there are physical parameters underlying this 21 centimeter data. I can't write down a simple equation for how to relate the data to the parameters, but the parameters are there and I want you to tell me their values. That's a good task for machine learning. And so a number of papers have been written on this where we can use an image-based analysis, a convolutional neural network, and analyze images of that 21 centimeter signal. So the first approach to do this back in 2019, one simplification they made, take a step backwards for a moment, instead of looking at this as a 3D volume, carved it into, say, 30 slices. Actually pick 30 slices along the Z direction, and instead hand 30 images to the network. And so what this convolutional neural network would do, as I said a little bit quickly earlier, is take those 30 images, convolve them, reduce their dimensionality, all the way down to very abstract, simple features. And so here's 5 of the 30 input images. And these authors showed that, yes, with this approach, you can recover the underlying parameters. Now, I should say, this is what we're going to be looking at in the workshop in a little bit. Rather than try and do anything 3D or even something where we're looking at multiple images, we've set up a case study where you're going to be handed kind of one of these images and asked to classify how much neutral hydrogen is there in the image. So early in cosmic history, the entire universe is neutral. As those stars and galaxies form, that neutral fraction goes down and down and down. So we want to regress on the actual value of the neutral fraction based on these images. I should say these units, we call this, it's a temperature, but we call it a brightness temperature. It's just a way radio astronomers like to talk about signal strength. So when you see your data in a little bit, your images will look more or less like this with a brightness temperature, and we're going to be asking, how can we recover the neutral fraction out of it? Now, since this 2019 result, there's been a number of different improvements on this kind of analysis. Recurrent neural networks, or even doing a 3D convolutional neural network rather than slicing this into different images, have been shown to provide modest improvements. But overall, one of the real strengths of the 21 centimeter signal is that there's so much information in it. You don't really need to build an optimal network to get a lot out of it. That as long as you built a pretty good architecture, you can do these regression tasks and recover the underlying physics because the signal is so rich in the physics. Now, I should also mention there's been a lot of work. So these are some results from Dr. Chowdhury, but a lot of work on non-image-based regression, trying to reconstruct statistical parameterizations of the 21 centimeter signal. This is an example on the left, we call the global signal. An example on the right, we call the power spectrum. But again, the idea is that these machine learning approaches are proving to be very good at reconstructing the underlying physics of the 21 centimeter signal. A number of different avenues. Where the challenge comes in here at least at the cutting edge of research, is that simulating reionization is difficult. Right? We need a training set. If we want to regress on images of the 21 centimeter signal, well, we need images of the 21 centimeter signal to train on. And we're going to get those from simulation. We don't have the data right now. And even if we did, we don't have ground truth for that data. This is a relatively well-known plot in the field where each column shows a different method of simulating the 21 centimeter signal. So again, time is going down here. And what you see are those bubbles. So when that very early simulation was light blue, carving away the black signal, here the color code is unfortunately the opposite. We see black carving away the light blue signal. But as time goes on, those ionized regions grow and grow and grow. But these three different simulations are asked from the same initial conditions, predict the evolution of the 21 centimeter signal. And while they agree on the large scale features, your eye can find some nice things. There's kind of this double bubble here. It's here in this simulation too, but a lot rounder. Here it's smaller. The different approximations made by these three simulations lead to different answers. And I should say we have to make these approximations. If you want to simulate this from first principles, it's absolutely impossible. We need a volume of the universe, a huge volume of the universe, but the sources of the ionizing photons are stars. So that's about a 1 part in 10 to the 17 dynamic range between the source of the photons and the size of your box. And computationally, you cannot simulate 10 to the 17 pixels on a side of a three-dimensional box. And so the question we have to ask, are the approximations underlying these simulations good ones? And more importantly, do they yield generically reproducible features? So what I mean by that is, if I train on simulations, will I expect my network to work when I give it real data? And our initial hints are no. So this is an example of a similar plot you'll be making in a little bit. Here's just another statistic describing the 21 centimeter signal. It's a number we call tau. But what we're looking at here is we simulated a bunch of signals with a known value of tau. We've asked a neural network to predict the value of tau. Blue dots here are a case where it worked pretty well. The orange dots are a case where it didn't work all that well, right? What this orange dot here means is, well, the real value was 0.6, but our network told us it was only 0.05. And the reason the blue dots here work and the orange dots don't, well, we have a network that was trained on simulations. And we call the simulation was trained on Z-Reion. And when we give it more Z-Reion simulations as if they were the data, it does a very nice job. When we give it a different simulation, called 21 centimeter fast, and it's the name of the simulator, pretend that was the data, it doesn't know what to make of it. It gets this biased answer. And it seems that even though, again, when we look at this plot, the different simulations produce things that to you and to me, I can see the similarities between them. I can say, yeah, these are describing the same physics. It's the same signal. It's the same universe. When we run the neural network, those differences seem quite important to it. And so active areas of research is, how do we reconcile that discrepancy? It may be that one simulation is just better than all the rest, and that's the one that we should use. But more likely, they're all approximate, they're all making errors, and they all have something to tell us when we finally get to the problem of analyzing real data. And so this question of generalization is an active area of research. How can we, using the simulations we have to make training sets, how can we do something that we're actually going to trust on real data? So that's kind of, in a nutshell, what I wanted to cover. We have these 21 centimeter experiments. They've been operating for a long time. I didn't mention this, but I've been working in this field for about 15 years now, and we have not detected the 21 centimeter signal. It's a very hard experiment. The foreground challenges, the radio frequency interference challenges are significant. We're making progress, but we still have a ways to go of removing contaminants, foregrounds, and RFI before we can detect the 21 centimeter signal. A lot of that progress has been driven by traditional approaches, improving traditional algorithms. But I would say these two examples, but other places as well, AI or ML is poised to deliver some significant breakthroughs for this field. The biggest problems are training set uncertainties or incompleteness, when we have no ground truth, or when we have ground truth, but we also know it doesn't look like the real data is going to look. Those are problems that we need to tackle. But if we can, I think these algorithms are going to be very successful in driving this field forward. So I will wrap up there. As I said, we've got plenty of time for some questions before we move on to the workshop. Folks want to post in the Q&A. I can try and answer any questions that folks have. Or I don't know. So I should say I'm not watching the slide.
Sorry, Jonathan, it's Rick. We've been looking at the chats. Right now, there's nothing in the QA, but if people would like to post something, please do. Can you see it under meeting chat,
Yes.
Jonathan?
So unsupervised training is a really intriguing area, right? When you don't trust your training set, well, don't have a training set. We're not quite there yet. I would say some of my collaborators and I are working on what we call weak supervision, where rather than providing a here is the ground truth training set, providing heuristics. So one example of a research project we have is using all the different radio frequency interference techniques that exist and treating every single one of their classification, yes, this pixel has RFI or no, it doesn't, as a vote on whether the real data has RFI or it doesn't. And building a training set from those heuristics. But some of the purely unsupervised approaches are not areas we've really explored yet.
There appears to be additional questions now. Oh, sorry, it's a link. Sorry, link to presentation. Yes, sorry. Wahid has answered that one.
Apologies for not getting that set up on Indico earlier.
No, it should actually be linked. I'm somewhat puzzled that.
Okay, well.
We'll work on that. I'm sorry. It should have been linked. Okay. So we customarily take a 5-minute break between the talk and the hands-on component.
Okay, well that sounds great. Then let's take a breather for a couple of minutes. If folks have any more questions, like go ahead and throw them in the chat. But then Dr. Chattery will take us through this example problem of regressing on the ionization fraction. So we'll see you all momentarily.
Okay, so let's say, well, given we're partway through this, let's say 10-2, just so everybody has a chance to. I realize everybody's in potentially in different time zones, but it's 10 to the hour, so it's about 6 or 7 minutes from now. We'll we'll pick up again. But as Jonathan says, he's very kindly agreed to keep answering questions if anybody has some. And I'm just gonna have a look at this link issue.
Sorry, I was wondering if there was an issue with my camera. I've just fixed it. But yes, I see a couple more questions. Again, we'll take a break. I'll start off by answering those, and then we'll move on with the workshop at 10:02.
There's one question in the chat box.
Oh, yes. Well, let's let everybody have their break, and then maybe I can do another minute or two answering questions when we all come back.
Okay, that will be better. Okay.
Okay, well, my clock says 10:02. I see a couple questions in the chat. Maybe I'll just spend a minute answering those, and then I'll pass it to Dr. Chowdhury to start talking about some of the workshops. So all great questions in the chat. The first one is whether we could get away from radio frequency interference, or at least human-generated interference, by going far out in space. It was a great question. So you're absolutely right to say far. Near the Earth is a terrible radio frequency environment. All the emissions from the Earth just hit you. It's extremely bright up there, but we also need a really big telescope. And so launching something very, very large far away in space is challenging. But what people are exploring are building something on the far side of the moon. And I could talk for another hour about that because I'm very excited about this idea. But building a radio telescope using the moon to block the Earth and shield us from those emission is potentially a future experiment for the field. So the next question is whether unsupervised training can help in understanding or emulating some of the features of the bubbles during the EOR. I think, to go back to an earlier point, I'm really excited about what unsupervised training can do. And I think these are areas we haven't explored so much as a field. And I should say there in some ways is a sociological challenge, which is with the brightness of the foreground emission compared to the 21 centimeter signal, there have been cases where analyses trying to remove foregrounds have also removed 21 centimeter signal and not realized it and misinterpreted the results. And that's happened a couple of times in the last 15 years. And so the idea of training something without a ground truth, where potentially what seems to be a very, very small error in the total signal is actually a complete catastrophic misinterpretation of the 21 centimeter signal, has people wary. And so I think it's a promising area, but sociologically, maybe we're all a bit too skittish to go all in on that just yet. And then last questions, regarding some of the ML model on RFI, whether the order of the images matter, whether we're talking about it as a time series, as a great question. So if, for those of you who have access to the slides, on slide 13, I said there's a little image of our data that goes into the pipeline. And while one of the axes of that image is absolutely time, we actually haven't really taken advantage of longer time correlations than that. So the fact that this little postage stamp is followed by another 2 minutes after it, those images are thrown in completely separately, treated as completely separate images. And so there's potentially room for improvement in looking at longer time series. And so I see one more comment that I need to read, but I think this is a good point to pass it over to Dr. Chowdhury. But thank you all again for your attention, and I look forward to working on the workbook with you all.
Thank you, Jonathan. 。 So if people would like to refresh their Indigo, they will find the link directly to the workshop shared drive. I think it was also posted by a colleague into the Metarima. You put it in. Thank you very much. There's a direct link also in the chat as well, if anybody's having difficulty finding the workbooks.
Well, hello everyone. I think, shall we wait for a few more minutes before we start the workshop session?
No, I think we're good. We're
We're
on.
good?
Let's keep
Okay.
moving. Thank you.
Okay. So this is the second workshop session for the day. And in this session, as you've just learned about 21 centimeter cosmology in the previous talk, we will be building a simple 2D convolutional neural network to predict the neutral hydrogen fraction from differential brightness temperature images. So if you click on the link provided to you to the shared drive, you'll see that it contains these folders, these files over here. Essentially, we will be requiring this particular file, the training set, test set, and the notebook. So what you'll do first is you'll make a copy of these three items in the folder by just clicking on make a copy. And if you go to it makes a copy in your own Google Drive. So once you go to your Google Drive, you'll find a copy of these three files, which we'll be requiring for this particular session. So there's a general instruction that we can remove this copy of part from these file names so that it'll be easier to work with the files. So you right click on the file and rename it and remove the copy of part from the test set and the training set. Right. So I hope you've all been able to access the notebook and you have it on your screen. So this is this image which you can see. If you look at the section which is titled Dataset Overview, you'll see three images. So these three images are all the same slice. It's a slice taken from one of the 21 centimeter simulations. So these are differential brightness temperature maps. The one on the left, which is labeled as this 512 cross 512. This is a delta TB map of the highest resolution which we have from the simulations from which we have made our training sets. So in this particular notebook, we will be using, you can see that there are two files, one labeled training set and one test set. So the training set consists of these downsampled or coarsely gridded images of these 21 centimeter temperature maps. So associated with each of these temperature maps, we have the neutral hydrogen fraction, which is labeled as XH. So in this particular example, we have an XH of 0.33, which means that the ionized map corresponding to this particular brightness temperature slice will be having 33% of the matter there will correspond to neutral hydrogen. Or you can say in other words that the 33% of the image that is provided to you that is containing neutral hydrogen, and the rest of it is ionized. So similar to this, we have several such slices which we have combined together and prepared in our training set, which is in this file. So essentially in this particular notebook, we will be looking at how we load and pre-process the data. We will plot a few samples and see how these training dataset samples look like and their corresponding XH labels. Then we will be building a network, simple 2D CNN. Then we will learn how we will be able to evaluate the performance of such a model. And finally, we'll see if the network is good enough to use, or we need to fine tune other hyperparameters and proceed with it. So this is a 2D, it's a regression problem, as Dr. Pober had earlier described in his talk. So here, corresponding to each of those image slices, we will be predicting a number which is not just classifying it into a certain category. It corresponds to a value, a percentage. It's in our case, it's a value which ranges between 1 and 0. And XH of 0 means the hydrogen fraction is 0. That means the universe is completely ionized. And the other way around, when the XH is 1, it means that the universe is full of neutral hydrogen. So we build our network in such a way so that we are able to predict these particular neutral hydrogen fraction given any brightness temperature map. So if you have to go through the text that is given here for your reference, and you'll find several links to the Keras modules. We use Keras in this particular notebook for as the backend. So let's begin. The first thing that you need to do is mount the Google Drive. So as soon as you click on this, you'll be probably asked for permission to connect to your drive. You give all the permissions, and then we move on to the next steps. So in this next cell, you have to, we had saved the files in our personal Google Drive folders. So essentially you have to replace this add your file path with where you have saved your files, which in my case is in /content/drive and my drive. You can check after your drive is mounted whether the file is there or not by just typing in ls and looking for the files. I hope you're all with me until this point. Now we move on to importing necessary packages and modules and loading the files, which I just mentioned, which is the training set and the test set. I hope all of you have been able to load the test and the training set, because this will be used in the next cells. So firstly, we look at the columns, what the training data consists of. So as we had just discussed a few minutes back, it contains a delta TB map, which is labeled as DTB map, and the corresponding XH. So just to look at how each of these delta TB maps looks like, these are temperature maps and they are coarse grained ones. So this particular one has a XH of 0.49, and you can see this is how it looks like. You can look at some other slice and see how it will be. And so this is the data which we will be training our network for. So our this will be the training data, and the targets will be the corresponding XH. So the first thing we do here is we need to pre-process the data. So we dump the data into NumPy arrays. The Keras models usually takes in NumPy arrays for functioning. So this is an essential step. So over here, we have just dumped the XH and the DTB maps from both the training and the test data sets into the corresponding XTrain, XTest, YTrain, and YTest. The next important thing in building any neural network or a machine learning model is normalization. So over here, we use a min-max scaler as a normalizer. So we scale the images. We apply this particular scaler on the input images as well as our targets, and we scale the entire data set. So this normalization is very essential. It scales down the values to in a uniform manner so that the network understands it better. So next we move on to how we set up the CNN model. So the CNN essentially stands for convolutional neural network. So it has a convolutional layer, a max pooling layer, and several other fully connected layers. You can have batch normalization layers and other hyperparameters associated with the model, which we will be tuning in as we progress to see how we get a better performing network for our particular task. So over here, I've listed some of those hyperparameters, which are parameters associated with the CNN model. So each of these can be varied as per each and every combination of these parameters would lead to a different kind of an architecture and a different model. So ultimately, as a user, we need to find the best possible model given our data, looking at how the model performs on different kinds of test sets or with different, according to our problem as we have formulated. So here are certain links for the detailed documentation of these all of these items. You will find them covered in very much details and along with examples if you look into these particular sites. So this is the cell which we will be building the neural network in. So we have just defined a function here, which is called build CNN model. This input shape refers to the size of our inputs. In our case, we have these 64 cross 64 resolution images. It's a set of images, but each of the input files is of this particular shape. The next one is the filter parameter. So over here, we can give a tuple of the number of filters that we want to build our CNN with. The next one is the kernel size. This kernel size is also a particular parameter which we use to move across the image to look for features and extract features from the given input image. Pool size is also another parameter which corresponds to the pooling window. Then there are dense units and output units. In our case, our output unit will be 1 because we will be predicting only one particular value of the neutral hydrogen fraction corresponding to each input image. And by default, we have put these particular values over here, learning rate and output activation functions, etc. You can change these values and run it for a better performing model if you want. So here in the first step, we built the sequential model. And as we had defined the filters over here, so depending upon how many such layers of filters we had chosen, we will be adding a convolutional layer corresponding to the filter size, then to the kernel size, and have a kernel initializer and an activation function. These are all might be seeming as jargon to many of you who have not been who has not used these before. But let me assure you that if you look into these particular links, you will find very detailed explanation of these particular parameters and how they can be used in different kinds of models. So similarly, we build another set of layers where we have the dense units. So here is the particular model summary when we build a CNN with input shape of this 64-64-1. And for our case, we just have two sets of filters with a kernel size of 3 cross 3 and a pool size of 2 cross 2. So over here, if you look at the model summary, you'll be able to see that this is the first layer. And then we have the batch normalization, the max pooling, and the other set of conf2d batch normalization and max pooling again before we flatten the outputs from these layers. And then we have the dense layers. And ultimately, we have our final layer, which has only one output neuron, which will be predicting the XH. So if you have any questions, please put them in the Q&A or the chat box. So this training, which we'll be doing in this particular notebook, it's a very short one. We just run it for 100 epochs. It will take hardly 2 minutes to run, given the resources from Google Colab. So over here, for a better network, you might want to run this particular network for a larger number of epochs. You can change the batch size and look at how the network will perform. So as the network runs, you can print out these values at every epoch, which shows us the loss, the metrics, the MAE and MSE, which is mean absolute error and the mean squared errors, and the corresponding validation losses and validation metrics.
Madarima, while we're waiting for it, are you able to increase the font size just a little bit in the Colab, just in the browser? Maybe it's just me, eyesight and all that.
Font size.
It's marvelously small, but I don't know. Just tell Google. Is it a Google browser? You just need to tell the Google browser to. Oh yeah, sorry. Yes, you've managed to hide. That's clever. You've hidden the browser.
No, I can remove it here.
Bingo.
Yep.
Yeah, no, that's it. You just had. If you just zoom in a tiny bit more.
I can do this, right?
Okay. Yes. You're telling Colab to go large. Okay. No, that's great. Whatever.
Is it better?
People, may not have the issue, but I think it got larger. Yes. That's.
I can increase it. Oh, I'm so sorry about this.
No. I'm sure other people just blew it up. I was limited to how much more I could blow up the Zoom. That was all. That was great. No, thank you so much. I just figured we had a moment while it was epoching. I think it's finished now. Sorry, I've disturbed you. Carry on.
Yeah, it's fine. So this model has been trained. So it just took a minute. A little more than a minute. So now what we have to do is we have to evaluate this particular model and see, maybe we can look at the metrics and find out how, if this model is good enough for our purpose, for our task. So there are a few steps for evaluating a CNN model for a regression kind of problem. More or less, we look at the loss curves and we see if the loss curves are reducing, if the loss function is reducing over the number of epochs. And these loss curves are just graphical representations of how well our model is learning. So we have a training loss and a validation loss function, which we'll see in the next plots. There are other regression metrics like R2 scores, which is also called the coefficient of determination. You'll find a definition in the beginning of the this particular notebook. Then we have mean absolute error and mean squared error, which we are all familiar with. So these quantify the model's performance. The last thing which we'll be looking at are scatter plots, which I'll explain it to you as we come to that point. So we save the model, we save the history. The history part contains all of these metrics, the loss functions and the valid loss functions and the regression metrics, which has been used to build this network. So over here, we will be plotting the training and validation loss curves and the metric curves. So you can see in this first plot, we have a training loss which is going down with number of epochs. Number of epochs are on the x-axis, and the dotted curve is the validation loss. Similarly, if you look at the next plot, here in our network, we had chosen MSE and MAE as the regression metrics. So we have those two curves and how they have evolved. So essentially, even these two must reduce, go down as we increase the number of epochs. So we see over here that they have gone down quite quite a lot from the point that it had started training. So this just prints the values once again. So now we move on to how we will be predicting, how we'll be plotting the predictions on a test set. So we had saved a separate, we have a different saved test set, which we had loaded. So here we are, it takes it's a few milliseconds to predict. So over here we have predicted the XH, which is the neutral hydrogen fraction. We have also saved the original values of the labeled data set, which we had initially, to compare the values with what the network has predicted. So we can see that comparison here. We have just saved it into a different file. So here we print a few of the headers, you can say, few files, and you can see that for different original XHs, what we can call the ground truth, which we have in this case, because they are from simulations. In reality, from when we try to do this on real data, we'll not be having a true value because we'll not know what the corresponding XH is for that particular map. So over here, we plot we get some kind of a scatter plot to see how the original and the predicted values are. You can see that this is a particular scatter plot corresponding to the data set which we have. So over here on the x-axis, we have the true XH and the predicted XH on the y-axis. This particular black line is the true line, you can say. So the more closer these points lie to that line, you can say that the model has been able to predict these values more accurately. So in our case, we've not done very poorly. We've got an R2 score of 80.85. So usually it is the value of the R2 score closer to 1. 1 is the ideal situation when the true and the predicted values are exactly the same. So the closer it is to 1, the better the network performs. So this is for this particular model, we have got a particular R2 score of 0.85. So you can save this model in your personal Google Drive folders. And you can repeat this process several number of times to see which particular combination of the parameters which you have will give you a better value of this R2 score and maybe a better performing loss curve and validation, loss and validation curves and the regression metrics. So in one of the models which I had trained earlier, we've got a pretty good R2 score of around 0.98. So this is also possible using a particular combination of all those hyperparameters which we had just discussed. So now I would really encourage you to play with the parameters and see what is the best model that you can get. The better the model will be, the more accurate the predictions are supposed to be on this same test set. That is the whole reason why we have saved the test set. So the next steps would be fine tuning the model, and yeah, this is an iterative process, and this is just an example of how we'll be able to build a simple 2D CNN and use it for any of our regression tasks. Thank you. If you have any questions. And I hope all of you have been able to run at least this basic setup.
That was very clear. Thank you. I'm just trying to see if let's see, we did have a question, 315, from Tom.
Yeah, right.
Does that make, sorry, that's in the
Tom-
meeting chat window. Yeah, in the
Yep,
chat window.
I see it now. So Tom asked a question regarding min-max scalar. Well, in this case, Tom is saying that this min-max scalar might not be the best approach. It depends from the from problem to problem. So in this case, we are not having 3 RGB matrices. We just have one matrix, which is 64 cross 64 in our case, and each pixel value contains the value of the brightness temperature. So it's equivalent to a grayscale image with only one value per pixel. So applying min-max, the value is just scaled down between 0 and 1. So for this particular problem, min-max scalar works fantastically. If you're actually dealing with RGB matrices like you've suggested, definitely there are other kinds of scaling functions which you should be using. You can also customize and build your own scaling functions to deal with such images.
Thank you. There was a question from Hanshi, 252. Maybe more of a statement than it was a statement about XO 200. Is that one you saw? I think you were talking while that one came in. Is that one you think you can address? Sorry, I should give you time to read it.
I'm reading it right now.
Thanks.
I think that might have been a follow-up to some of the things I was saying after the break. But yeah, no, I think that's an interesting thing to look at. I will have to see what I can make of it, but thank you for the suggestion.
Yeah.
Good. Okay. If there aren't any further questions, then obviously, as you strongly suggest, people should go back and rerun and tune, experiment with the very nice workbook that you've provided. Thank you. That was extremely instructive. Otherwise, I think we can draw to a close at this point, unless there are any more. Please, if there are any more questions. But otherwise, if you already have, free to copy and experiment with the data set. We have the Slack.
The Slack channel as well.
Slack operating as well. We're going to lose the questions in the. Another question came in actually.
With an ANN.
Yep.
Well, we are dealing with 2D images over here. So how will you be making an ANN work? That it depends on the problem. See, basically over here, we do have a 2D matrix. You can build an ANN as well instead of a CNN, but then our simple neural network will not have these properties which we have used in a 2D CNN, the convolutional layers trying to find out features from an image. So those points will be missing if we are trying to use a simple MLP or a simply without any convolutional layer, if that is what you mean by using ANN instead of CNN. There's another question from Tom again, just to clarify, so the image is grayscale. Okay, there are no classes. Maybe a better way to put it will be, it's a matrix of information where each and every pixel is containing the value of, it has a numerical value. So each pixel belonging to how many classes, if I can understand your question correctly, if you are comparing it with RGB values, here you can just consider it to be one particular value with a minimum and maximum of that we can't really define very clearly from the brightness temperature maps, because it is a physical quantity which we will be able to measure. So the range would be varying. You can say the minimum can go down to probably a few hundreds of kelvins. And it's a physical value over there, so we cannot really define the number of classes in such a kind of an image. Yes, it's a continuous value. Are there research done on how application of filters to improve the result? Well, you can work with different kinds of filters and different types of filter sizes. I'm not aware of any research done on how these filters will improve the result, but this is a very simple task. You can play with the filters and see how the results will improve. And it does not take a lot of time. I'm assuming that application of filters, by application of filters, you are just referring to the filter size over here, which we had defined, and the kind of filter that we are using. Yeah. Over here.
Thank you. Should we draw to a close at this point, or is there? I think well, obviously, if any more questions, please put them into the meeting chat. Otherwise, as we were just saying, there is the Slack channel which has permanence. So if anybody has any issues with running code or getting access, do please raise item in the appropriate channel there. We'll keep looking at that. Otherwise, 10 o'clock Eastern tomorrow is we'll be meeting again. So it's going to be the same format that we've been using, except tomorrow that we're actually going to be looking very specifically at what's referred to as boosted tagging in a particle physics LHC scenario. Very different though from the today's unsupervised learning discussion in that context. And then in the afternoon, it's going to be specifically focusing on sort of galaxy morphologies or galaxy finding relating to data in the Vera-Rubin, the LSST telescope. Again, a very different application, but I hope by seeing so many different implementations in various different areas of application that you're getting a better and better idea about the capabilities of these certain machine learning inspired approaches. Okay, and Madhurima, thank you so much, and Jonathan, thank you so much, both of you, for excellent session. That was extremely useful, and also for all the work you put into the to the worked example. That is it's very elegant. Okay, thank you a lot. Thanks a lot. So we'll be shutting down the Zoom shortly, and then pick up again at 10 a.m. Eastern tomorrow. And thank you, everybody, for your thanks. It's much appreciated. Much
Thank you
appreciated.
all.